Hi, my name is Marius Rotter. I'm at my first semester in electrical engineering at ETS, and we're here representing SynapsETS, a scientific club that specifies in building and developing brain-computer interface. I'm with
Giancarlo Tayeg. I am also in my first year of electrical engineering, and the two of us here are here to present our project, which is MICSA, which stands for Machine Interface for Cognitive Signal Analysis. For our project, we have decided to develop a PCB which would incorporate the acquisition, treatment, transmission, and interfacing of the certain brainwaves, specifically alpha waves. But yet, unfortunately, due to certain issues we have encountered, we had to brainstorm new ideas, and using open source projects, we have been able to develop more and more complex and advanced circuitry.
the most complicated part and time-consuming of this project was to find and learn all what we needed to make it possible. Because being in the first semester or first year, we didn't have all that we needed in electrical, in medical science. So we started some research. We researched how the brain was functioning, how it was delivering its electrical signal to the skull, and how we needed to capture that. So with all that, we started our first draft, our first schematic, with only the first section, the amplification and the filtering. We knew that the brain was emitting about 20 microvolts to 100 microvolts, with a lot of noise, because we had long cables, and we have the power source that's delivering about a unwanted 60 Hertz. So we also knew that there was going to be a lot of filtering. So with all that, we managed to find a way that was plausible to have one low-pass filter just before the amplifier. It's a passive low-pass filter because we didn't want to have a lot of pieces and having a big board. So it's a low-pass filter that's filtering all the frequency above 40 Hertz, because we only wanted to have the alpha frequency, and alpha frequency is about 7.5 Hertz to 13 Hertz. So we started with a low-pass filter just before our amplification. In the first iteration, we have a couple of amplificational small module that were going to give us a full amplification of about 10,000 times. But we found a much simpler way of doing it with one module, a instrumentation operational amplifier, the INA 118. That's a module that's able to deliver a 10,000 gain with low drift and low noise at its output. After that, we knew that there was going to be a bit of a distance between our module, amplification module, and our analog to digital converter. So we decided to put another filter there, another low-pass filter, to be sure that we didn't have the 60 Hertz or all the frequency that we didn't want. After that, it's the ADS job. So we use the ADS 1299, a 24-bit resolution analog to digital converter, to be able to have the full spectrum of our signal. The problem we had was with the MCU. The MCU we used, the microcontroller we used, was the STM32F205 series. But unfortunately, we used a different footprint that we originally wanted. We used a BGA footprint. That's, as we learned it afterwards, a lot more complicated to use, and a lot less cheaper also to manufacture. So, but anyway, we managed to do something with it. And because we didn't know exactly how well it was going to be, we pin out all the output of the MCU to be able to use it afterwards to further research or to change some, to do some minor adjustment. We also had a lot of problem with the bias, because we know that, because with our research, we knew that we needed one, and the bias, that's the ground. But we didn't know how it was going to be implemented and how it was going to be really used. So we did a lot of research, and that was one of the most long research we've done, was to find out what's the purpose, the real purpose of the bias. And I think we found it. After that, after all the schematic done in Altium, we managed to, and all the power supply schematic too, because we need a 12 volt, minus 12 volt, 2.5 volt, minus 2.5 volt, and a 3.3 volt. So we needed a very complicated, well, not complicated, but a lot of different voltage. So we've done the schematic in Altium 2. We managed to make the PCB, the PCB footprint in schematic. Unfortunately, we don't have the PCB today due to some inconvenience with the MCU, with the problem with the MCU. We didn't have the time we needed to make it print and make it baked. So we only have the schematic today, unfortunately. But still, we're pretty happy with the result.
When it comes to reproducing our prototype, we have made all the documents available, such as the bill of material, the reference material, our schematics, as well as the Gerber files in the club's GitHub. So you'd be able to reproduce our prototype. In conclusion, due to the fact that we've encountered certain limitations during the development of our prototype, we have, such as the 3-channel interface and the MCU package, we have developed certain improvements, such as
changing, first of all, the package of the MCU to be able to have a board that's easier to make and cheaper. We also want to add a lot more of channel to be able to have a broader range of signal. We want to see to change some of the components to have a much higher precision. We also want to add in further prototype, maybe a wireless transmission for the MCU, coupled with a microcomputer on board, like a Raspberry Pi. We would like to thank our partners, Altium, Critias, and ETS.
And thank you all for watching.